So now I'm going to be talking about model selection. And I told you that we have various metrics for selecting model. You can use the AIC or BIC, and also have various methodology you can use for model selection. So now, first of all, I'm going to comparing AIC and BIC. You can see we have 5 models here. So the first one is just a single predictor, which is age. The second one is age, LWT. The third one is age, LWT, and smoke. Then we also have age, LWT, smoke, and race. So these are 4 models. And the fifth one is the full models, which includes all predictors. We're going to follow then create a comparison table. So this particular comparison table now, you can see we're having a data frame. Then we're going to be comparing these models. So we're going to be having these columns: age only, age and weight, age, weight, and smoke. Then age, weight, smoke, and race. Then the full model. So these are the variables, column names, or the variable names we're going to be having. So the number of predictors is also another column. Then this is the R squared of each particular model that we have. Then we also have the adjusted R square. Then we also have the BIC. We also have the AIC. So I'm just going to run this particular code here. Then I'm going to model comparison. So you can see in terms of R squared, the best model is actually the full model. So because we've already included all the predictors. In terms of the adjusted R square, it is still the full model, but you can see the value of adjusted R square have reduced, which means some variables were not actually significant there, which inflated the R square. Then in terms of AIC, we thought that the AIC with the lowest value is usually the best. So you can see it's still the full model. And also in terms of BIC2 also, it is still the full model that is the best. So these are, you can compare various models. So you can just use this code as a template when you're trying to do yours. So let's compare the AIC and the BIC. So we want to calculate the change in AIC and the BIC. I already explained the change in the AIC and the BIC. You can see it, which is just what we just did there. So we did the delta AIC, this is the delta BIC. So you can see the lowest is still actually the full model. It's one with the lowest change in delta AIC. So we have the forward selection. With forward selection, you can use the step AIC function for forward selection. So this is going to start with a single predictor up till it takes all the predictors and finds out the best model. So I'm just going to run this. So you can see you just give your model null, which is your first model that you're giving. This is your model null. Then you give your scope, which is your model null and model full. So we are giving the scope now. The model null does just have only the intercepts. The model full has all the predictors. So we're telling it where it should stop. Then the direction should be forward. Then trace is equals to true. I'm just going to run this. So when we run this now, you can see, let's just get it full. So you can see now we have our coefficient. So I've already run a forward selection model. So this is the final result which you can use. So it's not going to include all the predictors. It's going to include, you can see most of the predictors are actually the significant predictors. So the same thing is also the backward selection. You also use the step AIC. The only difference is that this time around the direction is going to be what? Backward. So we're going to start with a full model. So until it removes all the predictors that are not actually significant. So you can see for the backward selection, this is also the final model. So this is the model forward. So you can see the model forward and the model backward are somehow different. So some predictors are not actually there, which are in the forward and also in this particular backward. So these are the differences you can see. Like you can see now, the backward model is having the adjusted R square 0.2154, and the forward model, if you go back to the forward model, we're having an adjusted R square of 0.214, almost similar adjusted R square. So which means that the models are almost the same, just that the predictors actually they are different. So stepwise goes back and forth, which you can specify in direction as both, using the same step AIC function. So you just give your scope, both the null and the full model to be your scope, and you run it and you get a stepwise, you can see almost also the same R squared. So this is now the stepwise model. So you can compare both models to see the value of the AIC. All of them are having almost similar AIC. Now model validation, I also explain model validation. This is more or less like a machine learning technique. So you always make sure you want to set seed. The reason for setting seed is that you want the situation whereby anytime you run analysis another PC or someone runs your code, it gets the same result as you. since sometimes random numbers are generated, or random numbers actually used to split the data into two. I'm going to set the seed as 1, 2, 3. So if you try changing this seed on your PC, you'll find out that you have a different splitting than compared to mine. But if you set it exactly like this, you have the same splitting to me. So we now take a sample. You can see we're going to take a sample from the data, and what we are trying to do now, we are trying to create a trained data by taking a random sample of 1 to the number of rows of the birth data. So, but we are taking the size of 0.7 times the number of rows, which means 70% of the observations in the data is what we are interested in as our training data set. So we are taking it randomly. That's why we are using the sample function. Then once we do that, we now have our trained data. This trained data, okay, let me just run the training index for you. You can see, set the seed, then run the training index and our test data. So this is just the index. We are taking a random index of it. So we're now going to apply this index to subset our training data and also subset our test data. So I take head of trained data and head of test data. You can see we have two different values, as you can see it here. We have this and also have this. So this is our training, this is our testing. So we're going to be running the model on the training, and we will now test the model on the test. So you see we are running our model currently on the train, which is this, and we are going to predict from the training model. We're using this particular code you are seeing here. Then we'll calculate the performance metrics and also the residual tests. So these performance metrics are going to show the performance of the model. That is the training model. Then residuals tests. So these are residuals, the difference between the actual and the predicted values. So what is our root mean square error? Our root mean square error is also a way of measuring the performance of your model. We also have the mean absolute error, MAE. Then also have the R-squared test data. So the R-square on the test data now, we're trying to see the performance of the model. So our final R-square now is now going to give us 0.02359. So this is our final R-square, which is very low, which means our model is not that great. So we can actually plot the predicted versus actual, which is the residuals. So you can see it is somehow scattered. So if all these lines should fall on this red line, it means we have a perfect prediction. Well, you can see how scattered it is, which means our prediction is not what? It's not perfect.